Gerardo Schneider. I come from the same group as my colleague Wolfgang there, who talked earlier, but I'm from different university. So I'm not from Chalmers, I'm from University of Gothenburg. And I will be talking today about monitoring data minimization and something about some other similar hyperproperties. I don't know whether we are familiar with the GDPR, the new regulation that will enter into place now in May. This is about privacy. And among the many privacy principles that you have in that regulation, one of them reads like that: personal data must be adequate, relevant, and limited to the minimum necessary in relation to the purposes for which they are processed. And this is what data minimization is about. The question when you read about this is that there are many words, adequate, relevant, minimum necessary, purpose, that are not clear what does it mean technically. So whether or how this could be ensured. Can we do it statically? Can we do it at runtime? And this is the objective of this talk. So what is the scope? We are considering here programs with a single input and output in principle. Of course, we are aware that this is much, much more complex. In fact, you can have multiple input that are distributed, could be dependent or independent, could be geographically in different places, etc. And of course, the program, as you know, could be very complex. It could be a program with side effects, might be communication, could be concurrent. For the sake of this talk, we'll keep this simple, and I will come back to the extension of this later. Another thing that is very important to clarify is the scope. Data minimization, it's not only concerned about collection time, but also about processing. And that is where the purpose and the usage enters into place. And in this talk, I will focus on the collection part only. So I have divided this lecture into two parts. The first one is to understand data minimization and what can be done statically. And the second part is the monitoring part. So let's go for, in the first part, how we can define and characterize data minimization from a language perspective, programming language perspective. Minimality talks about purpose, as we have said. In this talk, as we are not modeling purpose in a specific way, we are considering that the program, the functionality of the program, is the purpose we are going to consider. So let's see a very simple example, just to understand the main basic concept of data minimization. Let's assume that your program P just receive as input a salary and compute whether the person providing the salary have access to certain benefits or not. And it's a very simple check. If the salary is less than 10,000, then he or she has the right to the benefit, otherwise doesn't. So the idea is that you will input the salary, will get false in this case because it's 12,000 and there is no right for benefit. If it is 5,000, will be true. If it is 90,000, it's false, and so on. Yeah, very simple program. We input data, we observe the output, and of course, the program should be giving the right verdict on whether there is access or not. So from the functional point of view, it seems this is correct. The question is whether is this program minimal or not. And for that, we have to come with a definition. So is it the salary really needed here? And I think for this simple program, you already realize that really not. Yeah? So this is somehow our first understanding or starting point, is that we try to give a definition of data minimization based on this input-output relationship. And we are making an assumption. We are considering only deterministic programs. They're functions, but not functions in the pure sense of functional programming. And the main objective then is to determine whether this given program is minimal or not. If it is not, whether we can minimize it. So this is the whole objective. So for people coming with a security background, there are these basic concepts like strong dependency that goes back to 76 introduced by Cohen, that says that the output of a given program is strongly dependent on the input if some variations of the input has impact on the output. These concepts have been used later by Gauguin and Messeguer a few years after that to define a very well-known concept in security called non-interference. And non-interference, the objective is to show that there is no strong dependency between the input, in this case, inputs that are considered secret or high from the security point of view, and the public output or low concept. So you don't want to see flow from high variables to low variables, because you can learn secrets essentially. And this has been the basic concept behind many of the information flow security line of research. Now, one important remark here is that this kind of definition usually define sufficient conditions. So the low input is sufficient to compute a low output. You don't need high. This is what you aim. Yeah? Data minimality, it talks about necessary and sufficient conditions. Why? Let's see. Let's define first a total dependency. That is a variant of a strong dependency. So we can define total dependency in this way. We say that the output of a given program is totally dependent on the input if any variation in the input is reflected in the output. Yeah, such contrast against strong dependency. The only difference is this quantification here. Yeah. So the idea probably becomes already obvious to you now is that total dependency is very much related to data minimality. Yeah. And this is exactly the definition we have, that a program is minimal if the outputs are totally dependent on its input. Why is that? Yeah, you want to collect as much information as possible, but exactly the information that you need for the computation, no more, no less. Yeah. So it's a kind of duality with this notion of non-interference. We have two variants of data minimization based on whether you have only one input, this is a monolithic case, or whether you have multiple sources that eventually are independent. So you don't assume any kind of knowledge between the different sources. And then we call that distributed. For the monolithic case, the definition also, if you are a mathematician or have taken your basic computer science course, you know that minimality is just injectivity. For any input should be just one output. Yeah? You cannot have two inputs that go to the same output. So it seems quite trivial. We will see, not in detail later, but the distributed case is much more complicated than that. Okay. Let's take again this benefit program. It's clearly non-minimal, as we have seen already. All the red values here map to false, and all the only black here maps to true. Yeah? So the question is, can we minimize? Can we do something to obtain minimization? And we don't want to touch the program. For the time being, this is a black box for us. So the idea is to define a preprocessor on the client side. Here you're assuming that the program is on the server side. And in such a way that this preprocessor filters the input so the program only receives minimal data. And again, for the monolithic case, I think that you can assume that this is quite easy. So what I will do is whenever I see a certain value bigger than the threshold, I will give an arbitrary value, 100,000 here. When I see something that is less than 10,000, that was the threshold for the benefit, I give 1,000. And I always give the same representative. Yeah? So I'm filtering the input, choosing representative in such a way that here, if you now observe P, taking a look at the input and the output, you cannot disclose any information about the real input. You are minimizing data. Is it clear? Yeah. So we can write the minimizer, and the minimizer is exactly that. Check whether the salary is greater or equal than 10,000, give 100,000. If it's less, give 1,000. Yeah? And this is this program here, M. Now, we have, of course, studied some algebraic properties of this composition. They're quite trivial. The first one is that this preprocessor that we are defining does not change the functionality of the program. Yeah? If you compose M and P, the behavior is the same as P. And the second one is that you cannot minimize more. Yeah? So you can put more minimizers, you will not get any gain. And then you can have many processors, preprocessors that define this property. We aim at the best one, the one that really minimizes the best. Okay. Other property, for those of you who have studied the theory of programming, is that exactly what you are computing here is the kernel of the program. And the kernel, what is? The kernel is a set of all the inputs that maps to the same output. This is a notion that already exists since a long time ago. Yeah? So you can give a characterization by saying that the minimizer is a program if and only if it has exactly the same kernel as the program. I think it's pretty trivial observation also. And not that trivial, but there is a result saying that for any program that is deterministic, as we have seen before, there always exists a monolithic minimizer. Okay, I will not go into the proof of this. It's an observation, so you can always get a minimizer for a program of that kind we are looking at. Okay, so what happened in this distributed case? It's a little more complicated. First of all, what is the definition? There are many candidates of defining distributed minimality. Let's start with one. So one definition could see this, assuming now that we have two inputs, and you have these two vectors representing input, and what you want to do is that what happens is you differ just one. This vector has many inputs, and you just differ in one of them, and the rest is equal. And you want to be sure that the output is different. This seems reasonable. It seems to be a generalization of the monolithic case. Yeah? Okay, let's take an example. Very simple function, XOR. All of you know this function. Is it distributed minimal? According to this definition. So what you should do to check that, in this case it's easy because there are a finite number of possible cases. You take all the possibilities where one of the parameters is the same, in this case the second parameter, and you just make a variation on the first one. You apply the function to these two input vectors, and if it is different, you say, yeah, okay. For the time being, satisfying the definition. But you should do it for all the inputs and output, yeah? So now you, again, fix the second one, true, true, and then you just make a variation on the first one. The output is again different, so that's okay. Now you take the first parameter, you fix it to false, and you make a variation on the second one. Oh, again, you get different, and again with the last time. So indeed, under this definition, the XOR function is minimal, distributed minimal. Yeah? But it's not monolithic minimal. What does it mean? that if you consider now the vectors to be as if were from the same source or not independent, that means you can observe the two inputs, yeah? And you take it as a vector. You say, this is my only input to the program. It's not, because there is a case that is not monolithical minimal. There is a case where the inputs are different, but the output is equal. So somehow we found that if we try to generalize this concept of monolithic minimality to the distributed case, we cannot in general, because we will exclude programs like this, and that doesn't make sense. So that's why we came with a weaker notion. That is the definition that I gave. But still it's too strong. Why? Let's take another very familiar function, the OR function. Is this distributed minimal? Okay, somebody says no. Why? Yeah, indeed. So it's very clear that it's not distributed minimal, because it's not possible to minimize this either argument without really in an independent way. We have to know something about that. And this is the example, yeah. You would take the second parameter is fixed, it's true. This is a variation here, but you get the same value. And of course the symmetric case is the same. So if we want to capture minimality for programs like the OR function, then of course we need to come with a new definition. And this is what we have. The first definition was this one. We now call it strongly distributed minimal, because the second notion that we have is weaker. And the second notion is this one, where we relax this condition by saying, well, can I find a value on the other parameters such a way that I can make this output different? Yeah? And indeed, this definition captures this, and the OR now is distributed minimal. Yeah? Because given the situation that we had before, I can always find a value for X to make this output different. Yeah? So we are happy with that. We have also some results saying that well, for any program there exists a distributed minimizer, and we have this relationship between these three notions. Okay, so far so good. Now, this is privacy security. So usually you have to come with the attacker model. You have to explain, okay, what they're really trying to solve, and how come you can claim that, okay, what happened, what is your model of attacker, yeah? And we are using this idea of having a program in parallel, so the attacker has the same knowledge as the program, even if it can make a copy of the program. And the idea is, if I put it in parallel here, can I learn more? Yeah, I can have the full functionality of P. And in fact, you cannot. Yeah, you cannot, because the minimizer guarantees that filter the input and the output that you observe, that doesn't tell you anything about the original input. So we can say that we are secure with respect to this attacker model. Okay, so this is, before I conclude this part and go to the monitoring part, I would like to say that we have tried to compute this minimizer. What can we do statically? And for doing that, we relax this condition of being black box, and we try to be white box, so we have access to the code, and implemented this into this tool chain here that essentially takes a Java program. It takes a JML specification, as you have seen in Wolfgang's talk. We give it to key, and then we can even annotate with invariants, etc., other conditions if we want. And then the idea is that we do a symbolic execution of that, and we extend conditions over all the possible paths that you have connecting output and input. This is symbolic. We don't execute the program. Yeah? So you get a big formula characterizing all the possible paths. And we give this to a solver, Z3 in our case. The solver will try to solve it. If not, of course, you have to help the solver. And then you obtain the equivalence classes, the kernel, and we choose a representative. So essentially the step I have shown before via example, we have implemented. and then we get a minimizer. So you extract a program that is a program that will put as a preprocessor and guarantee that will minimize the data. Okay, and then of course we took case studies, one monolithic, one distributed to see whether it worked well. So what are the limitations of this approach? First of all, we have some assumptions. Yeah? We are taking relatively simple programs in the sense that we are assuming this is deterministic, and for the moment we don't consider side effects. Yeah? So it's just input, output, and then if there is side effect, the side effect is considered an output. Yeah? You can consider that anything that you save in memory is an output. The distributed case could be refined even better, because for the moment we consider this or monolithic or distributed where the sources are completely independent. But it could be that maybe you want to allow certain partial knowledge between the sources. We are not doing that. And then obviously the last picture I showed you, the whole procedure is undecidable. So you cannot do completely automatically. Mostly because as soon as you have loops, you need invariant, otherwise you cannot obtain. Even if you have invariant, it could be that this is too big. Your program might have a lot of loops and nested if then else, etc. It could be unfeasible. In theory, yeah, you can always interact with the tools and you can get it. In practice, we know that it's hard, as hard as doing program verification in general. So it could be very costly. Also because in principle, very much you want to consider all the possible inputs, and that might be hard in certain domains. Okay, so obviously these are limitations or optimistically further work, so we still have to work there. So this is a summary of this first part. We have defined data minimization as a variant of strong dependency for deterministic programs. We have provided some criteria on how to determine whether the program is minimal or not, and we gave the semi-decision procedure to get the minimizer, and based on symbolic execution and such solvers. Okay, so this concludes the first part, that it has no runtime verification, no monitoring at all. Okay, so let's go to the runtime monitor now. So why do we need monitor? Well, statically, we cannot do much, as you have seen. Yeah, we have this semi-decision procedure. We need the source code if we want to get the minimizer using this technique. And that means that in general, you cannot apply if let's say that you promise me, you say, no, yes, I take your data and I promise you that we are satisfying the data minimization principle. I don't trust you, don't give me my code, I don't have a way to check. So of course, monitoring is the next step, natural step, when I have to consider black box approach. So can we do this? Well, of course, the first step is look into papers. You go to literature. At the beginning, to be honest, we did it in the inverse order. We first did the thing, and then we realized that, in fact, there were some papers about that. And there are a lot of papers, among others, some of our colleagues sitting here, famous researcher Cesar Sanchez. Yeah, now I got your attention. And Bern also, Finkbeiner, who is also part of this cost action, and other people, among them Bouzou, who has done quite a lot of work on runtime verification of these kind of properties. So what are the results that they get there? Well, the first paper is a paper by Cesar, Bern, Michael Clarkson, Collaney, and other people there, about defining, extending LTL for hyperproperties. I will come back later, but maybe I don't come back later, I tell you already now. I'm introducing a new concept here, hyperproperties. So if you have not heard about it, a hyperproperty is a property over a set of traces instead of one that is defined over a set of traces. LTL talks about set of traces. But most security properties, you need to see more than one run in order to talk about it. Non-interference is one of them, for instance. So they have given algorithms for that. In particular, they have results for model checking, decidability result for model checking, But what concerns us here is the result for monitorability. And they have algorithms for alternation-free fragment of hyper-LTL. Hyper-LTL is this logic that extends LTL over adding quantification over traces. And alternation-free, that means that you cannot have for all exist, for all exist. You can have only for all or only exist, as many as you want. Okay? So monitorability for, if you only have for all, you cannot monitor for that, but you can monitor for the negation. But this is not a problem, yeah? If you want to monitor for something, you can negate the formula and monitor for violation. So it's okay, but it's important to see that if you give me a for all, in general, I will not be able to monitor that. Okay, that's nice. So what is the impact it has on our research? Well, that's great. Yeah, data minimization, indeed, it is a hyperproperty. You can write it in hyper-LTL, so that's good. Yeah. But then we say, oh, all the weeks and months that we spend finding this very nice result, it's just a particular case of something that some other smarter people did. So, okay, what do we do? Well, but wait a moment. This is for the whole hyper-LTL. We're interested here in very specific subset or fragment of the logic. So we got some hope. We said, well, maybe we can get something better. And this is what I will show here. How to come back and say, okay, now we have this notion of monolithic data minimization, strong and distributed minimality. And let's try to do monitoring. Knowing already that the for all, we cannot monitor, and the exist, we can. Yeah, so this is a very low resolution. But the idea here that we try to express data minimization then as a hyper-LTL formula. And as you can observe, here we have quantification over traces. Remember, this is hyper-property. And this is only, this I, subindex I, is the projection on the input. And this O is projection on the output. So what this formula says is what was written in English before, is that if I take two traces that the inputs are different, I should, when I observe the outputs for that corresponding input, the outputs also should be different. So this is the definition in hyper-LTL for data minimization. In fact, there is a fragment that we try to look at many other security properties, and we realize that all of them enter into this small fragment that we call hyper-LTL 2S for Q safety. There's a concept of K safety property. I will not go into that. And it's not very important, the syntax, because I will not be using that very much on the rest. It's just to relate to people knowing hyper-LTL. So no minimality is monitorable, but not minimality. Traces here are very specific, because remember, we give an input, we observe the output, or we give a set, a vector of input, and we see an output. The traces have length 1. We are considering deterministic programs, though most of the result in general, in practice, most of the programs are deterministic in the examples that are around on hyper-LTL. And the property only talk about input and output and relationship between these. So it should be simpler to monitor than just to use the existing algorithms for hyper-LTL. So let's see this in an example. Just a comment before that is that we are trying to go from the hyper-LTL, where we have very single traces of size 1, a trace is 1 input, 1 output. We put the program in a loop. We prove that we preserve the property, so we can see this as a stream. So we transform a hyper-LTL into just a monitoring something on traces, not on set of traces. So essentially, when you have this program, remember we have seen before, the monitor what sees is a stream. It will see the pair input-output. It will say OK. It will see the next pair will say OK. And then we see this one, it will fail. And it will fail essentially because I have observed 2 elements in the trace where they have the same output for different inputs. Okay? So, what is the monitor? The monitor is very simple. You read the input, observe the output, and record this. you record this in a table. You do the same. Yeah, remember the program in the loop. So you do exactly the same. If it is okay, you continue doing it. If it's not okay, then you say, okay, you have violated. So we detect non-minimality. You cannot say anything about whether it's minimal or not. Okay, is it clear? Very simple monitor for a very simple property. The intelligence, of course, is in the OK function. Yeah, I mean this is a skeleton of a monitor. And for the for this monolithic minimization, it's very simple. Is there a prefix with the same output and different input? It's quite trivial to check that. Okay. So, for just give an example again for this. Whenever the example of the benefit program, we will observe 1,200. We observe false. Under the input 5,000, we observe true. This is okay. 90,000 true. It will fail because it will detect that there is a prefix that does not satisfy this, and then we'll say, okay, you violate, the program is not minimal. Good. So, what happened with the distributed case? It's very similar, in fact. Okay, so for the distributed case, the okay it will be different, of course. Remember, we have two notions of distributed minimality. One is stronger, and it's easier to do that. The other one is more complicated. In fact, we cannot monitor for the other one. And there are some theoretical results on this, but I will not go into that. So, okay, we took data minimization. We have a very simple monitor for detecting the monolithic case, a little bit more complicated, but still manageable for the distributed case. And yeah, is it that very interesting or not? And in fact, it turned out that there are many properties that are very similar to data minimization, so we can reuse a lot of what we have done for these other properties. For instance, non-interference, integrity, and software doping. And I will say a few words about these three. There are more properties. This is the one that we have definitely studied and analyzed. But most of the security, we had difficulty to find a property, a security property among the interesting one that has three quantifiers. They must exist, but we didn't find. Non-interference. The definition, one definition, there are many. One of them is this, that a program satisfies non-interference if every pair of traces with the same initial low observation remain indistinguishable. That means that you should not be able to detect or have that the high influence the low output. There are different ways to put it. Two other ways to put it is that this definition I gave at the very beginning is the absence of a strong dependency between input that considered high and output that considered low. Or even another way to talk about this property is that the public output, the one that you observe, that everybody can observe, by low security users should only depend on low input. And then in hyper LTL2S can be written like that if you observe, project only on low input and they are equal, then you should observe the same low output. So you can read this in many different ways. You can take the contra opposite, etc., and you get all these variants. Okay, so this is in the fragment, so we can use the same monitor for that. Integrity. Integrity says that the high behavior, secret behavior, or something that you consider confidential, should not be influenced by low input, because this low input can be manipulated by attackers. Another way to put it is that traces having the same high input but possible different low input should have the same high output. And this is captured by this formula here. Again, the projector on high in the input, the projector on high in the output. You see that all these formulas have this very, very nice, it's just implication of equality or inequality. So they're very, very similar in a certain sense. Finally, doping-free programs, a new concept after the diesel scandal. Informally, the idea of a doping free program is that small variations in the input should give small variations on the output. The whole idea is that, yeah, you should not be something manipulating and something, oh, now we got low consumption, even though you should not have gotten that. There are different variants of the definition. The definition we used the one based on a parameterized program where you define the parameters that are of interest to you, and then you can write this property into only considering a projection only on those parameters. And essentially, again, what you get is a typical implication that when you observe two traces, and you say the input is equal, the output should be equal, but only for the parameter of interest, that are the parameters that you can tweak and eventually cheat your program. So you can see in this table we have the definition, we have the property we have considered, data minimization, both minimality and the strong distributed minimality, and non-interference, integrance, and software doping. All of them can be written in this fragment. Okay, so these properties are there, and now the question is if you can use the same technique as we had before, and indeed we can. As we said, the intelligence is there, so they have the same shape. And the only thing you do is of course, encode the properties here. And what are these encoding? When this encoding is essentially taking the part, you take away the quantifiers, you take that as a condition, and this is the check that you, and this is how the monitor was implemented. It's implemented in a parameterized way. That means that you give this condition as a parameter, and then you can check many properties in the family. So not very important clarifying note here. We have here before that the standard way to do runtime verification in this community is that you come with a property, usually in a logic, and you automatically extract the monitor from that. And this is, we have also done that in another work using Larva and things like that. But we don't extract the monitor here from the property in this traditional way. But what we do is that we start with a template, and then we pass the properties parameters. So it's slightly different. And I mean, like Martin, I put a small commercial here. Do not only use regular LTL, but also use automata. I think automata give you more expressiveness in certain sense. So I'm coming now to the enforcement that you talk. We couldn't find a way to do enforcement online for this kind of property, but you can do it offline under certain assumptions. So you have your input domains. I wrote here only 2, but you can have as many as you want, and you have your program. And the idea is that offline, under the assumption that your domain is the finite input domain is finite, sorry, input domain is finite, then you can generate, of course, all the possible combinations. You feed the program. You can observe that with a monitor, and you can definitely give a final verdict, because this can be done exhaustively. And not only that, you can also generate the minimizer for data minimization. It's not clear that you can do it for the other properties. Okay? For data minimization, we have a black box approach, and we can get the minimizer, the same minimizer that we showed before, very complex, for using symbolic execution and using SAT solver, etc. So it's quite nice. Of course, you can say, well, is this realistic? Maybe yes, maybe not. There are examples where yes, it makes sense. I didn't talk about optimizations. If you have knowledge about the output, you can do even better, because if you know that the output has only 2 values, true or false, then you only need to observe, traces until you exhaust some. You try to force to get something different, but how many runs can give you false? Only 1. How many runs can give you true? Only 1. So you can do even better if you have more knowledge. We have not done that. We have only took this assumption of finite domain. Okay. So summary of this part, the second part. We got this parameterized monitor for this fragment, only for violations, not for the positive. The result that we presented, these properties, all of them are input-output, so of length 1. But theoretically, you could extend this for any other property where the length is bounded. Because the key issue here is the transformation that I didn't talk very much. The transformation of a hyperproperty into a normal property by collapsing these multiple traces, gluing the traces into one. Another property that all of these have is that the order is not important. So even you don't need to preserve the order. If you have a property where you need to talk about the order, something that happened 3 before or 3 after, then of course you cannot do that because here you just put all of them, and then if you run the program and you give this input in different order, you might get that your property may be satisfied sometime, maybe not. But for any property where the trace is bounded, finite, and where the order is not important, can be monitored in this way. The complexity is quadratic in the length because you have to always go back. For any input, you have to go back and revisit all in worst case, the whole prefix. You can optimize. For data minimization, there are clear optimization of this. And then if you have this assumption of the finite domain and eventually additional knowledge, you can do the enforcement offline. And in particular for data minimization, that is not the case for the others, you can extract the minimizer. Okay, so let me acknowledge this. This is a joint work with 2 postdocs. Thibault, who left now, he's working at CEA in Paris now. And Srinivas, who recently left to Indian Institute of Technology. And Dave Sands, as I said, a colleague at Chalmers from the security community. The first paper, the first part that I presented is in a paper where we introduce the concept of data minimization. The second one is a technical report on study deeply on the algorithm monitorability of data minimization in particular. For instance, there we have result that for strong distributed minimality, we can monitor the violation of that, the non-strongly distributed minimal. But for the weaker version, in fact, none of them are monitorable because there is an exist. Remember that we need to observe that there exists some place where we can, and we cannot do it. And finally, this generalization of this for hyperproperties in this subclass have been published recently, accepted recently, formalized. Okay, an advertisement before I finish. I'm looking for a postdoc on privacy, and this is very open. If you're formal method, language, or researching on programming language or privacy security, just contact me, send me an email. But you should be, of course, interested in privacy. Deadline for application of 15th of April. And the idea is that you start September or maximum at the end of the year, because otherwise I cannot promise to pay you 2 years, because the grant will expire in 2020, December. Yes, okay, that's all.